Now let's look at a formula that you will need to know. Let's look back at our pancakes. Let's assume that when we're making our pancakes, we spill some of the batter, burn a pancake, drop one on the floor, or somebody comes by and eats some of the black batter. There may be other uncontrollable events that happen, so in the end, rather than making 15 pancakes, we only make 11. The actual amount of product that we make in a chemical reaction is what's known as the actual yield. And we can determine the efficiency of making pancakes, or any chemical, by calculating the percentage of the maximum number of pancakes we actually make compared to what we should make. So the actual yield is what we actually get. The theoretical yield is what we should get. And remember, the theoretical yield depends on the limiting reagent. We take this fraction and multiply it by 100% to get a percent. This is what's known as percent yield. So if I look at my situation where I had 11 pancakes made, that actually made it to the table, when I should have had 15 pancakes, I multiply that by 100, I see I get a 73% yield. If I made 15 pancakes, then I'd have 100% yield. If you make what you should, you get 100% yield. But usually in chemistry, for reasons that are sometimes beyond our control, we usually make less than the theoretical yield. Now let's remember, the theoretical yield, based on the limiting reagent, will always be the least possible amount of product formed. Because after the LR runs out, we can't make any more. And again, because of both controllable and uncontrollable factors, the actual yield of the product will almost always be less than the theoretical yield. So typically you're going to have less than 100% yield. Now we've seen this throughout our stoichiometry. We know that in the lab our balances don't measure moles, they measure grams. However, stoichiometric ratios require moles. So when we're dealing with experimental data from the lab, mole to mass conversions are commonplace. We have to do them all the time. And you'll have to do them as well. So let's look at this example that pulls everything that we've looked at in this chapter together. Here we have a balanced chemical reaction. Copper 1 oxide reacts with carbon to produce elemental copper and carbon monoxide. When 11.5 grams of carbon are allowed to react with 114.5 grams of copper 1 oxide in the reaction below, 87.4 grams of copper are obtained. From this information, find the limiting reagent, the theoretical yield, and the percent yield. As always, to help us organize everything and to help get our thoughts started, we want to write down what we're given, including the units and the chemical formula. We're given 11.5 grams of carbon, 114.5 grams of copper 1 oxide, and we're given that 87.4 grams of copper is produced. Then we want to write down what we want. We want the LR, we want the theoretical yield, and we want the percent yield. Well, we know that the limiting reactant and finding the theoretical yield are something that we can find out in the same process. But to do that, we have to do stoichiometry. And if we're doing stoichiometry, we're using our stoichiometric coefficients that come from our balanced equation, and these are in moles. So I've got to get my grams to moles. So the first thing I want to do after I write everything down is I want to calculate the molar mass of everything. I'm going to need the molar mass of all of these. Because these are all in the equation. I'm going to need stoichiometry to get my mole ratio, and to get between grams and mass I need the molar mass. So the molar mass of copper 1 oxide is 143.02 grams per mole. The molar mass of copper is 63.54 grams per mole, the molar mass of carbon 12.01 grams per mole, and then I'm going to use this to figure out my limiting reagent, the relationship between my two reactants and my product. Now I'm given information about carbon and copper 1 oxide. I'm also given information about copper. So copper is the product that I'm going to choose because eventually I'm going to use this information to calculate my percent yield. So when I do my ratios, I'm going to do both my ratios for each reactant with copper. So let's see how my units play out. I have grams of carbon, grams of carbon, grams of carbon 1 oxide, grams of carbon 1 oxide, moles of carbon 1 oxide, moles of carbon 1 oxide, moles of carbon, moles of carbon, moles of copper, grams of copper, grams of copper. Now in this case I'm going to have an extra mole of copper here because I've got to do my conversion 2 times. So this is the one time where it's not going to be this is the one example of when it's not going to be we're going to have 2 of each because I've got to do this conversion 2 times. So what do I mean by that? Well, let's take a look at figuring out our limiting reagent. To figure out our limiting reagent, we take the amounts of both our reactants, our copper and our copper 1 oxide, and we see how much copper we get. So before we can do that, we've got to get our grams to moles. So let's start with our carbon. I have 11.5 grams of carbon, and I need to get it to moles. 12.01 grams of carbon is 1 mole of carbon. And now to see how many moles of copper I'm going to get, according to my balanced equation, 1 mole of carbon makes 2 moles of copper. So my grams of carbon cancel out, my moles of carbon cancel out. This tells me 1.915 moles of copper is what I get. Now let's do the same thing for my copper 1 oxide. I have 114.5 grams of copper 1 oxide. I want to get to my moles. Here's my molar mass. 143.08 grams copper 1 oxide is 1 mole. And now I want to see how many moles of copper that's going to get me. And here's my relationship right here. 1 mole copper 1 oxide gives me 2 moles of copper. My grams of copper 1 oxide cancel out, my moles of copper 1 oxide cancel out, and when I do my math, I get 1.60 moles of copper. So this tells me this is the least amount that I get, this is the most that I can actually make, this is my theoretical yield, and my limiting reagent is copper 1 oxide. So my copper 1 oxide is my LR. Now, they probably want our theoretical yield in grams, and we actually need to get it to grams to calculate our percent yield. So let's take this one step further and use our molar mass of copper here to get our theoretical yield in grams. Okay, so here I actually, in my previous slide, I didn't take it out to 4 sig figs, which I needed to, because my original value had 4 sig figs. And so when I change my moles of copper to grams, I get 101.7 grams of copper. This is my theoretical yield. Now the last question, or the last thing we need to do is our percent yield, which is actual over theoretical times 100%. So our theoretical is 101.7 grams, and then our actual was given as 87.4. So when I do the math, I get 85.4 0.9% yield. And that makes sense because it's less than 100%. And I have 3 sig figs because over here I have 3 and 4. And when we multiply and divide, our answer has as many sig figs as the value with the least number of sig figs.